This video will be focusing on part 1 of solutions, which is essentially discussing what are solutions, what are they composed of, and how can we determine if something is soluble or not soluble. So those are the two, and also electrolytes. So those are the three major topics that we will be discussing in this particular video. In the following video, which will be part B for this chapter, we'll talk about different units for concentration of a solution and why the concentrations are important. Okay, so let's begin. So the first thing is, what are solutions? What is the definition of a solution? So solutions essentially are homogeneous mixtures of two or more substances. So when they're mixed together and it forms a homogeneous mixture, homogeneous meaning it is uniformly distributed. All the substances that are mixed together are uniformly distributed throughout the solution. That type of a mixture is called a solution. So this is formed when there is enough force of attraction between the solute and the solvent molecules to keep it together. So those are solutions. For instance, if we take salt and we dissolve it in water, and as long as the salt is completely dissolved in water, that would be an example of a salt solution. Whereas if you take sand and you disperse it in water, it is not going to dissolve in water. It will be not a homogeneous mixture. It will be just a simple heterogeneous mixture. That is not something that we can call as solution. A solution has to be homogeneously mixed all over. Now, regarding solutions, the composition of a solution, it basically consists of two major components. One is called the solute and the second is called the solvent. Solute is the substance which is present in the lesser amount. That's the very simplest definition of the solute. Solution is composed of solute and solvent, and solute is the one which is present in the lesser amount, whereas the solvent is the one which is present in higher amounts. So this is higher amounts, and solute is the one which is lesser in quantity. Okay, now, here it's giving you the same definition again. Solute is the substance in smaller amount and the solvent is the substance in greater amount. Now, when we talk about solutions in total, they can be of many different types, and that would depend on what solute and what solvents we are mixing together. So for instance, solute can be liquid, gas, or solid. Whenever we talk about solution, we usually think we are mixing a solid into a liquid, but that's not true. Solute can be liquid, gas, or solid. They are spread evenly or uniformly throughout the solution. Solutes mix with solvents so that the solute and solvent have the same physical state. What this means is that in the beginning, solute and solvent can be of different states, but at the end, once a solution is prepared, both of those are in the same state. For instance, if we make salt solution, usually salt, which is NaCl, if you're making this at home, NaCl is the normal salt that we have, that is usually solid, whereas water is usually in liquid state. But when they are both mixed together and the salt is completely dissolved in water, they both are present in the same state. For instance, if this is salt solution, they are present in aqueous state. So at the end, solution has the in case of a solution, both solute and solvent will have the same physical state. And the important thing is that once the solution is prepared, we cannot separate the salt from water anymore just by filtration. Okay, so separation cannot be just a physical process. Solutes cannot be separated by filtration, but they can be separated by evaporation. So simple example is a salt solution. If you want to separate salt out of this water, you cannot pass it through a sieve or a filter paper, but only way you can separate them is probably doing heating this water solution up. Once it's heated, all the water vaporizes and the salt is left behind. The solutes are not visible, but they can give a color to the solution. So once the salt solution is completely made up, all the salt is dissolved, you can tell that you can't find the solute anymore. You cannot see the salt crystals anymore. Only thing you can see is that it looks a little bit turbid in color, right? So it can give it a certain amount of color, but usually it's not visible. So when we talk about different types of solutes and solvent, like I said, solute and solvent can be in multiple different states. For instance, their solutions can be gas solutions, meaning we have our gas and gas. Our solute is gas and our solvent is also gas. One example of that is air. Air is a homogeneous mixture of oxygen, nitrogen, hydrogen, helium, all those gases. So this is an example of gas in gas solution. Here the solvent would be the one which is highest amount, meaning nitrogen gas, and solute can be, for instance, oxygen here. Okay. Liquid solutions could be where basically our final solvent is liquid, but your solute could be gas. So meaning it's a solution of gas and liquid. Gas and liquid example would be, one common example that we use at home, soda water. What is it composed of? It has CO2 gas mixed in with water. So that is an example of gas in liquid solution. Liquid in liquid, fairly simple, vinegar. Vinegar is basically acetic acid. This is the chemical formula for vinegar. So this is the solute mixed into water that gives us dilute vinegar that we can consume. So this is an example of liquid in liquid. Solid in liquid, one easy example is seawater, which is salt dissolved in water. So here water being the larger amount is the solvent, NaCl is the solute. Next would be solid solution. So we usually think, like I said, solutions would be liquids, but that's not true. Solutions can be solid as well. As long as it's a homogeneous mixture, it is a solution. For instance, solid in solid would be alloy. For instance, brass. Brass is composed of both zinc and copper metal mixed together. So both of those are solid, and after finally mixing, that solution is also a solid, which is called brass. Similarly, another example is steel, which is a mixture of carbon and iron. So solutes and solvents can be solid, liquid, gases. It doesn't really matter. Okay. One very common rule that we can talk about, or rule of thumb in terms of solutions, is that like dissolves like. Like dissolves like, meaning like interacts with something that it is something which is similar to it. For instance, here when we say like, we are specifically talking about polarity of a molecule, a property of a molecule, which is polarity. Now when we talk about polarity, we can classify the compounds as either polar or non-polar. So what this rule tells us, that if you're mixing polar molecules, like dissolve like, that means polar mixes with polar molecules. And similarly, non-polar molecules mix with non-polar molecules. But if you try to mix polar with non-polar, that is not going to mix. Why? Because again, like dissolves like. Only like compounds like each other, they are going to mix with each other. For instance, if you try to mix salt in water, so salt in water is an example of polar mixes with polar. Salt in water, that would mix. Whereas if you try to mix oil in water, that is not going to mix. That will not prepare a solution. Why is that? Because oil is non-polar molecule and water is a polar molecule. So if you try to mix unlike molecules together, for instance, non-polar solute mixed with polar solvent, solution will not form. Similarly, if you do vice versa, your solute is polar and solvent is non-polar, the solution will not form. Only like molecules dissolve or mix with each other. Unlike molecules do not. Here, oil is non-polar, water is polar, so they are unlike molecules. But if you mix polar molecule with polar solvent, non-polar solute with non-polar solvent, they will mix with each other. Okay, for instance, if you take polar with polar, let's say a salt solution. So salt is a polar molecule, which is our solute. Solvent is water. Water is also a polar molecule. So polar and polar will make a solution. Non-polar and non-polar will also make a solution. For instance, if you take olive oil and mix it with grapeseed oil, those two oils, both the oils are non-polar, so they will mix with each other. So that is an example of like dissolves like, and unlike molecules don't mix with each other. Okay. Whenever solute For instance, an ionic compound is dissolved in water. That ionic compound usually forms is each atom of that ionic compound is separated from each other, and water surrounds that ion, which is called the process of hydration. Okay, so this process where ionic compounds dissolve in water is called the process of hydration, where each atom of the ion, for instance NaCl, each atom, meaning Na plus Cl minus ion, they interact with water and they are surrounded by water, and that process is called hydration. How does this actually happen? So for instance, if we say this is a crystal of NaCl where we have bunch of atoms of Cl, which is the green one, and bunch of atoms of Na, which is the purple ones. So water, we know, has a charge. It's a polar molecule because there is oxygen and then there are two hydrogens attached to it. And because of the electronegativity of oxygen, we know oxygen carries a partial negative charge and these hydrogens carry a partial positive charge. So when this crystal is dissolved in water, whatever atoms are on the edges or the surface of this crystal are going to interact with water first. Whatever is on the inside of the crystal stays inside, but whatever is on the surface interacts with water. So if there is a positively charged if there is a positively charged atom, like here, this is the sodium atom, it has a positive charge. So water, the oxygen atom on water has a negative charge. This negatively charged oxygen is going to interact with this positively charged sodium ion and slowly going to take it away from the rest of the crystal. And now this sodium will be surrounded by water such that these red atoms that you're seeing are all oxygen. Oxygen will interact with this positively charged ion because oxygen carries a negative charge, and so sodium ion is separated. Similarly, the chloride ion, for instance right here, which is present on the surface of the crystal, is going to interact with the hydrogen atoms of the water molecule because hydrogen carries a partial positive charge whereas chloride carries a negative charge. So these partial positively charged hydrogen atoms are going to interact with chloride ion and they are going to separate the chloride ion from the crystal, and they will be surrounded with these hydrogen atoms of water surrounding it, and chloride will be separated. So basically we start from the surface of the crystal, and as we go into the crystal, each water molecule interacts and separates the ion until all of this crystal is completely dissolved. So basically each water molecules basically are pulling each ion away from the crystal and hydrating each of them separately. Once all of these are dissolved, then you don't see the crystal anymore. So that is how exactly an ionic compound dissolves in water. The ions on the surface of the NaCl crystal are pulled into the solution and surrounded by water in the process called hydration. This process keeps on happening until all the NaCl is completely dissolved, and hydration of the ion diminishes their attraction to other ions and keep them in solution. Now basically this Na is surrounded by water. Similarly, this chloride is surrounded by water. So the force of attraction between Na and Cl minus is now reduced. Okay, so that is exactly how an ionic compound dissolves in water. And for a covalent compound to dissolve in water, water is going to form hydrogen bond with that with the hydrogens that are present in the covalent compound, and that would help in solubilizing those covalent compounds into water. Okay, now solution with non-polar solute. If you are making non-polar solute with water like a polar solvent, they are not going to interact. There will not be any force of attraction between the particles of a non-polar solute and a polar solvent, and that is why non-polar solutes will not mix with polar water molecules. Okay, so in order to mix non-polar solutes or dissolve non-polar solutes into a solution, we need non-polar solvents. Okay, the next topic we'll talk about are electrolytes. Whenever we talk about salt solution, one very common terminology that is used is electrolytes. And what is an electrolyte? It is a substance that can produce electrically conducting solution when dissolved in water. So basically, electrolytes are the solutions that can conduct electricity. The solutes that can, when we dissolve them in water, they are going to be good conductors of electricity. That is why they are called electrolytes. So if we talk about when somebody is like not feeling well, they have a fever, or somebody is getting dizzy, we usually talk about that they should consume more electrolytes. Why is that? Because in our body, electrolytes regulate our nerve and muscle function. Electrolytes are very important. They control the hydration in case of our body. They control what is the pressure of our blood. They control which chemical reactions will happen in our body and which will not happen in our body. Therefore, maintaining the level of electrolytes in our body is very important. Okay. So what are electrolytes? When we drink electrolytes, if you have ever seen the composition of those electrolyte solution, they majorly consist of ions. Ions like sodium ion, potassium ion, chloride ion, bicarbonate ion. Those are the major types of ions that make up the electrolytic part of our body solutions. Okay. So that's why they say sometimes you should just drink some salt solution, right? Because it consists of sodium and chloride ions. So an electrolyte is very important to maintain the level of the electrically conducting solutes in the blood. Okay. So now when we say electrolytes, there can be two different types of electrolytes. One is a strong electrolyte, another one is a weak electrolyte. What do electrolytes do? Electrolytes essentially dissociate in water. Dissociate means they break apart. For instance, if we take NaCl, which is solid, and we add it to water, it is going to dissolve and dissociate, meaning separate from each other to form Na ion, which is now aqueous, and Cl minus ion, which is now aqueous. So this process is called dissociation. Strong electrolyte basically will completely dissociate in water. So for instance, if you take a spoon of NaCl, you add it to water, a cup of water, that one spoon is going to completely dissolve into ions. That when something completely dissolves into ions, that is called a strong electrolyte. They usually can conduct an electric current very strongly. Okay. Weak electrolytes only dissociate slightly. For instance, if you take this HF into water, it will dissociate. HF is going to break apart into H plus and F minus, but at the same time, not all of it is going to dissociate. Some of it is going to still stay as HF. Those are called weak electrolytes. Such solutions are called weak electrolyte solution because there not all the salt has completely dissociated into its ions. They slightly dissociate in water and they would also conduct electricity but not as strongly as the strong electrolytes. So those are called weak electrolytes. And then there is something which is called a non-electrolyte. A non-electrolyte would be a compound which basically does not dissolve in water. It does not produce ions in water. It is not going to conduct any electricity. For instance, if you take sugar and you dissolve it in water, sugar is called sucrose, is the chemical name for sugar that we eat, cane sugar in our house. So if you take sugar and dissolve it in water, it will dissolve, but it is not going to produce any ions because this is not an ionic compound. So it is, as there will be no ions in the solution, it is not going to conduct any type of electricity. So those are examples of non-electrolyte solutions. They do dissolve in water, but they don't have any ions. They cannot conduct electricity, so they are not electrolytes. They are non-electrolytes. So let's try some questions. Complete each for a strong electrolyte in water. So if the question is telling you this is a strong electrolyte, it means it is going to completely dissociate into its ions in water. So calcium chloride solid in water is going to give us, it's a strong electrolyte, meaning it will completely dissociate into its ions. The two ions would always be a cation and anion. Here the ion is calcium ion. Calcium, it always makes its group number 2, so it will always be calcium 2 plus, and chloride is group number 7, so it will always be 8 minus 7, which is a negative 1 charge, and this would also be aqueous. And you can see each calcium chloride has 1 calcium ion and 2 chloride ions, so this would be 2 chloride ions. And remember, ions are always aqueous in solution. Like we saw before, ionic compounds dissolve in water and they get hydrated, so they have, each ion has water molecules surrounding it, and that is why it is called aqueous. The state now is called aqueous. So your answer here is going to be C. Next we have K3PO4. Again, the question is, it's a strong electrolyte, so you don't have to think this too much. Only straight answer is that it is going to dissociate into ions. What ions does this have? It has potassium ion, and it consists of this PO4 minus. Remember, it's a polyatomic ion, so PO4 3 minus is the phosphate ion. How many potassium? I see 3 potassium, so 3, and phosphate stays together. We only have one of those, so it will be 1 phosphate ion, and each ion is going to be hydrated, so they will be aqueous. So answer here is going to be A, 3 for potassium and 1 phosphate. Do not break phosphorus and oxygen apart from each other. This is a polyatomic ion. It always stays together. Next kind of question could be like this. Which of the following reaction represents the dissociation of a strong electrolyte in water? Again, we are looking for a strong electrolyte, meaning it will dissociate to give ions completely. And what you're seeing here in the first reaction, there is no dissociation happening. The products are not ions. Same thing in reaction number B. This is methanol in water. It's still methanol. It is aqueous, but it's not ionic in nature. Unless until it's ions, it is not going to be an electrolyte. It has to be ionic. Products have to be ions at the end. D is again an alcohol, but it is not dissociated. It is not ions. We don't see ions in products. Whereas for part C, we do see ions. Sodium sulfate dissociates to give 2 sodium ions and 1 sulfate. So answer is C. Next, write the equation for formation of a solution for each of the following. Now it's telling you to write a reaction, chemical equation for this. The dissociation of K2CrO4, which is solid, a strong electrolyte. So it's telling you it is strong. So you can simply break this into 2 ions. So this would be K2CrO4 solid. It will dissociate in water, which is liquid, to give us potassium ion. Again, this is 1 ion and this is a polyatomic ion. So CrO4 2 minus. This will be aqueous. This will be aqueous as well. How many potassium? 2. Now, one question you could ask me, how is this -2? How did I know that? Again, first thing, you should be able to identify it's a polyatomic ion. Next thing, we can assume if we don't know the charge, you could calculate the charge, just how we have been doing before when naming these compounds. So for instance, potassium always carries a charge of +1. And how many of these atoms do we have? 2. So 2 times +1 plus, we'll assume the charge of this whole anion is X. And total charge, sum of everything is equal to 0. Why 0? Because the compound is not charged. It's a neutral compound. Now we solve for X. So if you solve for X from this here, it would give you X is -2. That's how I know this is -2. Otherwise, if you have memorized this polyatomic ion, you would know it always carries a charge of -2. Okay, moving to part B, which is the partial dissociation of a weak electrolyte, H3PO4, in water. Question is already telling you it does not completely dissociate, it partially dissociates, and it's a weak electrolyte. So we will start with our compound, which is H3PO4. In water, it is going to give us hydrogen ions, which would be 3 hydrogen ions, because we have 3 of those, and 1 phosphate ion, which is PO4 3 minus. But since it's weak dissociation, you would show this as a double-sided arrow. It will convert, some of it will convert into proton and phosphate, whereas some of it will go back into its actual H3PO4 formation. So this, when you put a double-sided arrow, that you're showing, it is going both ways. It is a partial dissociation. Not all of it has completely dissociated. Next is dissolving of solid sugar in water. Now, you know, when you look at this molecule, this is not a ionic compound. So when you see that something is not ionic, you basically will only dissolve this in water. If this is solid in water, it is going to become, it will dissolve, and once it dissolves, it will become aqueous, but it will not dissociate. You can't break this into ions. So this is a example of non-electrolyte solution, which you, of course, the question is not asking for that, but the question is only asking for this particular reaction. Okay, the next topic we'll talk about is solubility. What does solubility mean? So for instance, if you take a cup of salt and a cup of water, a small tiny cup of water, and you start adding sugar into it or salt into it, NaCl into it, you will add 1 cup, 1 spoon, 2 spoon, 3 spoon, 4 spoon. At some point, no more salt will dissolve in that water, right? And that is exactly what solubility tells you. It tells you the amount of solute that can be dissolved in a specific amount of solvent. So this tells you how much solute, maximum amount of solute that we can dissolve in a certain amount of solvent. For instance, if you take NaCl, you add like 4 spoons, 5 spoons in a cup of water, and then it would stop dissolving. That means 5 spoons can be maximum dissolved in 1 cup of water. So that would be solubility of water. Salt in water. Okay, and now if I take the same cup of water and I heat it up, now maybe it's possible that I would be able to dissolve, instead of 5 spoons, I might be able to dissolve maybe 7 spoons of salt into that. Why? Because now the water is heated up, so molecules have more energy, and because of that they would be able to move around more, and we would be able to dissolve more solute into that solvent. Same amount of solvent can hold more solute. So when we talk about solubility of a solution, that is temperature dependent. As long as you're not changing the temperature, the solubility will stay same, but if we change the temperature, the solubility will also change with temperature. It's usually expressed as grams of solute in 100 grams of solvent. For instance, when we talk about solubility of potassium nitrate in water, it is given by 65 grams in 100 grams of water. This essentially means you could dissolve 60 grams of potassium nitrate in 100 grams of water. So basically I can use this information as a conversion factor now. If I have 65 grams of potassium nitrate, it will dissolve in 100 grams of water. So I can use it as a conversion factor to go from grams of potassium nitrate to grams of water when we talk about solubility. Okay. For instance, here if we want to figure out how many grams of water, how many grams of potassium nitrate can I dissolve in 120 grams of water, what can we do? We start with what's given, which is 120 grams of water, and we want to cancel the grams of water, so we divide by grams and convert it into grams of potassium nitrate. Now we use our conversion factor. Potassium nitrate is 65, water is 100. So here we can figure out how much potassium nitrate can you maximum dissolve in 120 grams of water. So this would give you an answer of 78 grams of KNO3. So basically this conversion factor of solubility will tell you how much amount of solute can you maximum fit into a certain amount of solvent. Now let's talk about different types of solution based on their solubility rule. Okay, so based on solubility we can have different types of solution. For instance, unsaturated, saturated, and supersaturated solution. Okay, so let's take some example. For instance, I have this cup of water like we used before, if we have 1 cup of water and we are adding salt into it, we said that the solubility of salt in this water is, let's say, 5 spoons in 1 cup of water. If this is the solubility of our solution, salt solution, and I start with 1 cup of water and I add 2 spoons into this, and that 2 spoons of salt into this, and that salt completely dissolves. Now this solution is called an unsaturated solution, where I have not reached the maximum amount of solute that is possible. Maximum I can add 5, I've only added 2 yet, so this is a solution of unsaturated salt solution, when your amount of solute is less than the maximum amount possible. Now let's say I take again this cup of water and I add 5 spoons of NaCl into it. This kind of solution is called a saturated solution, where we have added the maximum amount of solute into the solvent. So if I add another spoon of NaCl into this, it is not going to dissolve. That is called a saturated solution. It consists of the maximum amount of solute that can dissolve in there. Next type of solution is, let me take this solution. I will add 6 spoons into this. 6 spoons of NaCl into 1 cup of water, but I know it will not dissolve. So what I do, I heat this solution from to increase its temperature. Once you heat this solution, it is quite possible that all 6 spoons might dissolve into this, and this solution is now called a supersaturated solution. I dissolve 6 spoons and then I let it cool down. This solution is called a supersaturated solution. When a saturated solution is cooled down, it would consist of more solute than the solubility would allow. So at a room temperature, basically it can maximum hold 5 spoons. What I did is I added 6 spoons, I heated it up, it dissolved 6 spoons, but now I am cooling it down. So when you cool it back down, it consists of more amount of solute that it can actually hold, and that solution is called a supersaturated solution. Okay, next we'll talk about what is the effect of temperature on solubility. Like we saw before, whenever we have a solid, when you try to add a solid, for instance, you take salt, NaCl in water, you heat it up, it is going to increase solubility. You can take another example, glucose is a sugar. You add the sugar into water, it has a low solubility, but as you increase the temperature of water, more and more sugar will dissolve in water. This is temperature, this is the amount that is dissolving. So if you take NaCl in, Na3PO4, it's a salt. Slowly it's a solid, so as you add it, as the temperature of the solvent or water is increased, more and more of it will become soluble, right? So most of the solid, solubility for most of the solid increases as the temperature increases. But now in case of solids, the effect is this. In case of solids, temperature increase result in increase in solubility. But gases behave different. For instance, if you take a can of Coke and you leave it at the room temperature, and you open it up, leave it at room temperature, and then you have the same can, we open it up and put it in a pan and start heating it up, or you put it outside in the sun, which one is going to get flat first? The one that is put outside, the one that is in heat. Why? Because gas, as we increase the temperature, those gas molecules are going to escape. As you increase the temperature, the gas molecules will have more energy, they are going to escape the solution. So the amount of gas in water is going to decrease, which means the solubility of gas in water decreases as we increase the temperature. So gases have an opposite effect. As we increase the temperature, the solubility decreases in case of a gas. Okay, and simple example is, you could take example of a can of soda. Okay, so simply take the soda bottle and can or bottle, you put it outside in heat, it is going to get flat first, but if you keep it on ice, let's say, it is going to take longer for this bottle of soda to lose all the carbon dioxide. So that explains the effect of temperature on solubility of a solution in when the solute is solid or when the solute is gas. Gases decrease as the temperature increases. Okay, so questions that answers can be explained based on this is, why would a bottle of carbonated drink possibly burst when it is left out in hot sun? Why would that happen? So if you have a bottle of carbonated drink and we put it outside, it consists of this gas dissolved in water. As the gas molecules gain energy, as the temperature increases, gas molecules, they are going to gain energy. More energy means more kinetic energy. More kinetic energy means they move around more rapidly. As they move around, they collide with each other and they collide with the bottle that they're kept in, which means it is going to increase pressure inside. Increase the pressure of gas inside the bottle, and that would cause it to explode. When it becomes unbearable for the bottle to keep the gas in, keep the pressure, it is going to explode. Next question could be, why do fish die in water that is too warm? Why? Because again, gases, solubility of a gas. As the water gets hot, solubility of gases in water. Gases in this case is, we are talking about air in water, decreases. Why? Because gases have more energy now, they are going to escape from the water. So solubility decreases, which means now fishes would have less of that air to breathe, which means they would die. Why does a cup of hot water dissolve so many more teaspoons of sugar than a cup of iced water? Why? Because when we increase the temperature, the solubility we saw of solid increases. Solubility of solids increase. So we could dissolve more of those solids into our cup. Okay, the next over here we were talking about solubility with respect to temperature, how solubility changes when we change temperature. Next we'll talk about how solubility changes when we change pressure. This is explained by Henry's law, which states that solubility of a gas in liquid is directly related to pressure of that gas above the liquid. At higher pressure, more gas molecules will dissolve in liquid. Okay, so Henry's law tells us at high pressure, more gas molecules dissolve in liquid. One quick example of that, you don't have to memorize it. It can be easily explained if you take example of a can of soda. So in case of a can of soda, when you open that can of soda, why is there that loud noise? That loud noise comes up because there is a lot of pressure that is present inside this can. Once we open that can, that pressure is released. Okay, so all that CO2 that is present inside this water is kept in. Why? Because that CO2 is under very high pressure. So when the pressure is really high inside the can, a lot of CO2 is dissolved in this soda water. But as soon as this is opened up, now this extra pressure gets released. So now this can of soda is under just simple atmospheric pressure. And because of that, that CO2, as the pressure above that can, above that CO2 soda has reduced, it is that CO2 which is dissolved inside that water is going to start escaping. It starts bubbling out of the solution. So fewer gas molecules are left in that can of soda. And that is exactly what Henry's law tells us. When there is a lot of pressure above the cola, the gas molecule stays in. But as the pressure is released above that cola by opening that can, less of the CO2 stays inside the water. So basically it tells us that at high pressure, the solubility of gas molecules in liquid is higher, and at lower pressure, the solubility decreases. Next, we'll talk about solubility. How do we know certain compounds dissolve in water and some compounds don't dissolve in water? So the compounds that dissolve in water are called as soluble compounds, and the compounds that do not dissolve in water are called insoluble compounds. Okay, So soluble compounds basically dissociate in water. For instance, NaCl, we saw NaCl will dissociate to give us Na plus ion, Cl minus ion, and it completely dissolves. Whereas insoluble compounds, they do not dissociate in water. They have a very low solubility. Only very small amount of it will dissolve. Most of it will stay as solid. So those are called insoluble compounds. How can you predict if a compound is soluble or not? This is the solubility chart, which can help you predict if an ionic compound is soluble or insoluble. Okay, usually you are expected to memorize this, but your exams are open book, so you could take a look at this chart and figure out if something is soluble or insoluble. But you should know how to read this chart. Okay, so everything that is listed in this chart is soluble, and exceptions are given to you alongside. So positive ions, when we talk about compounds that consist of these ions, all of them are insoluble, all of them are soluble. For instance, group 1 in the periodic table consists of lithium, sodium, potassium, cesium, rubidium. All of these are soluble compounds. If an ionic compound consists of these cations or these positively charged ions, all those compounds are going to be soluble. There are no exceptions. Same is true if we talk about a polyatomic cation, which is ammonium. All these compounds will always be soluble. Similarly, all the nitrates and all the acetates, this is an acetate. All nitrates and acetates are soluble irrespective of what is the cation in that compound. No exceptions. As long as it's a nitrate, it is soluble. As long as it is acetate, it is soluble. Similarly, all chlorides, bromides, and iodides are going to be soluble, but there are some exceptions here, which is silver, lead 2 plus, and mercury. So in this case, if it is silver chloride, it will be insoluble. If it is lead 2 chloride, that would be insoluble. If it is silver with iodine, all iodides are soluble except when it is with silver, when it is with mercury 2 plus or lead 2 plus. Similarly, all sulfates are soluble. Exceptions are barium, lead, calcium, strontium, and Hg2 2 plus. So if, let's say, if we talk about barium sulfate, that would be insoluble. If I talk about sodium sulfate, that would be soluble. All sulfates are soluble. Exception is barium, lead, calcium, strontium, mercury. Okay. And when something is not soluble, you guys have already seen those in precipitation reaction. Those insoluble compounds usually form solids, and that solid is called as a precipitate. When you take two ionic solutions, mix them together, and it produces a solid, that is called a precipitate. For instance, if we ask you, can you predict what would be the products for this particular reaction? When you see a compound like this, you should know that this is an example of a double displacement reaction, something we have done before in previous video. So if you are not if you can't remember that concept, go back and look through the video of type of the reactions, type of chemical reactions. Okay, this is an example of double displacement where lead is going to now form a compound with sulfate. So this is composed of two ions, lead and nitrate. Now here lead is going to, and this is composed of potassium and sulfate. So this is our cation, this is the anion. This is the cation here, this is anion. So cation 1, anion 1. This is cation 2, anion 2. So cation 1 is now going to form a new compound with anion 2. And cation 2 is going to form a bond with anion 1. So now the products are going to be lead with sulfate. Lead is +2, sulfate is -2. So the crisscross charges will give us the compound of PbSO4. And the second compound it will form is potassium with nitrate. Potassium is +1, nitrate is NO3 to NO3 -1. So crossing over the charges would give us KNO3. Going back to this, lead was Pb2 plus and sulfate is SO4 2-. Crossing over the charges would give us Pb2 SO4 2, and we want the least ratio, so it will be PbSO4. Now the question is, what are the phases for these? Is it soluble? Is it not soluble? we saw in our solubility chart, all the compounds that consist of potassium are soluble. All the compounds that consist of nitrate are soluble, no exceptions. So if it is soluble, it will be aqueous. PbSO4, we saw that all sulfates are soluble, but lead was an exception, meaning this will be solid. So now if you mix these two solutions together, they are both aqueous, meaning you can see they're liquid. When you mix two liquids, this particular solid will start appearing, and that solid is called a precipitate. So this solubility chart can help you predict what would be your reaction products. Okay, so here again, this is